In this lecture, we look at falling near the Earth's surface. The acceleration of gravity little g is not constant. This free fall acceleration g changes because the Earth's density is not uniform. There is a much denser inner core, a less dense outer core, then there's a mantle, and finally the thin blue outer layer known as the crust. The dense core, if you're closer to the dense core or farther away from the dense core, say on a mountaintop or in a deep valley, that'll change the value of g for you. Also, a local variation due to, say, there is a void or a heavy body of ore near the surface can produce a change in g. Earth is not a perfect sphere. Matter of fact, it bulges a little bit at the equator. And also there's a centripetal force due to the Earth's rotation, which has an effect on the free fall acceleration of g. So if you have an object near the Earth's surface and the Earth is rotating, you take that into account, there's the force of gravity down. There's the centripetal force that making it move on a circular path. There is mg also. And these two added together must be equal to the force of gravity, because force of gravity is providing both the centripetal and mg. So m times the acceleration due to the centripetal plus mg is equal to m times the acceleration due to gravity. Canceling the m's, we get g is equal to a gravity minus a centripetal. So that if we look at the variation, say, from the equator to the pole, since the radius is bigger at the equator, g varies from something like 9.78 to 9.83 meters per second squared as you go from the equator to the pole, due to the greater centripetal acceleration at the equator, due to the greater radii at the equator. Let's look at an example of how a variation can help you in prospecting for uranium. You are looking for a large body of uranium ore embedded in some granite. If there were no deposit, just solid granite, your gravimeter, your G measuring device, would measure some value. How much would this value change if there was a deposit? Assume the deposit is spherical and has a volume of around 1 million cubic meters. This volume of granite has a mass of 2.6 times 10 to the 9th kilograms. Also assume that its center is at a depth of 50 meters. So if we draw the picture, it looks something like that. The density of the uranium ore is twice that of granite. So a sphere of ore is like having two spheres of granite occupying the same place. So the change in g is equal to the acceleration due to a single sphere of granite that size, the extra sphere due to the ore. So delta G is equal to the universal gravitational constant, big G, times the mass of a single sphere of granite divided by the distance d squared. When you plug in all the numbers, the values for the mass of the ore divided by the distance it is below the surface, 50 squared, and we get 7 times 10 to the minus 5th meters per second squared. A not very large change, but measurable with current gravimeters.